So let's begin by jotting down the title, note 6.5, Operation with Radical Expressions, and also reviewing this very, very, very important fact that we learned last week, right? You could have any type of radical. Doesn't matter if it's a square root, a third root, a fifth root, whatever type of root you have, you could rewrite it as a rational exponent. What is a rational exponent? It's an exponent that's a fraction, okay? Now, where does this fraction come from? Well, whatever power you had, right, this power is going to be the numerator of your rational exponent. And whatever radical you have, whatever root, whether it's a square root, a third root, or fourth root, maybe I should use a different color, whatever that root is, that'll be the denominator of your rational exponent, okay? So let's use this truth and let's simplify this third root down here. Okay, so again, right now it'd be a good idea it'd be a great idea to print out the notes before we actually start class. But if you don't have a printer or if you didn't do it, that's okay. Just make sure you copy this very important fact that any type of root to whatever base, to whatever power, could be rewritten as that same base with an exponent, that's a fraction, which that fraction will be the power over the root, okay? So we're going to use that truth to simplify this third root expression. But before doing that, I just want to review some basic rules of radicals, right? Back in Algebra 1, or maybe even in the 7th or 8th grade, we learned how to simplify radicals. We know that when we're multiplying two items inside the square root, you could actually split the square root to each of those items. When is that handy? Well, if you have the square root of 18, that's not a perfect square number. You want to rewrite it with multiplication so you could get a perfect square number. So when you split them, you could actually do that square root of 9, which gives you 3, and the square root of 2 stays. So that's a very important rule that you could split. You could take this one single radical and split it to each of the items. Not only that, you could use that rule backwards. You could have a radical times a radical, and if it's the same type of radical, right here, they're both square roots. If they're both square roots, you could put both multiplication of those two items together underneath that one single square root. Again, that's true for any root. If you had a third root and a third root, you could put them together with multiplication underneath one single third root. And that comes in handy, like right here, the square root of 8 times square root of 2. Neither of those are perfect square numbers, but when we multiply them together, we get a nice square root of 16. All right, so we are reviewing these simple truths about radicals because we're about to simplify this complicated, or not complicated, but a little bit more entertaining third root radical here. So again, because we have pure multiplication, 54 times x to the 6th times y to the 14th times z to the 3rd, I'm going to split up the third root on each of these. So I'm going to do the third root on the 54, the third root on the x to the 6th, the third root on the y to the 14th, and the third root on the z to the 3rd. So we have 54 right here, we have x to the 6th right here, we have y to the 14th right here, and z to the 3rd right here. So let's do the third root of 54. Now, this is not a square root. This is a third root. So the question is 54 a perfect cube number? Something times something, something times itself 3 times. Will it give us 54? No, it won't, right? So what we want to do is, like we did before, or like we do anytime when we simplify radicals, you want to rewrite it with multiplication to get what you want. So I want a perfect cube number. What is a perfect cube number? 8, right? Because 2 times 2 times 2 is 8. Or maybe 3 times 3 times 3, 27. So I'm thinking of these perfect cube numbers like 8 and 27. 8 times something, will it give me 54? No. How about 27 times something? Yeah, 27 times 2 gives me 54. So what I'm going to do is rewrite it as 27 times 2. And I am now going to split that third root. That way I could actually do the third root of 27, which gives me 3. And then I'm going to bring down the third root of 2, and I'm going to do that in blue. Third root of 2. Now, you can't do the third root of 2, so you just leave it. Do we all understand that simplification, the third root of 54? Can I get a thumb up if you do? Sideways if it's kind of, thumb down if you're thinking like, what the heck is going on? Okay, got some thumbs up. Some people are probably watching YouTube and not watching class. All right, there we go, thumbs up, that's good. Let's move on to this next one. The next one's even easier, I would say, because when when we think of the third root of x to the sixth, that's a power, that's a root. We could write it as a rational exponent power over root. So I'm going to write it as x to the sixth divided by 3, power over root. And 6 divided by 3, that's a nice, beautiful number 2. So that guy really just breaks down to x squared. X squared. You see, it's easy. But let's move on to this next one. The next one is really entertaining. This guy right here. Fun stuff. Obviously, we're not dealing with numbers here. We can't really think of perfect cubed numbers, but we do know that the third root is the power of 1/3. So back when we had square roots being the power of 1/2, we would want a power that's divisible by 2. But right here, it's a third root, so we want a power that's divisible by 3. Now, the thing is, 14 is not divisible by 3, but I want a power that's divisible by 3. And like on any other radical, when we're simplifying, if I don't have what I want, I rewrite it with multiplication to get what I want. So if I want a power that's divisible by 3, I want to go down to y to the 12th times y squared. Y to the 12th times y squared. Okay. And now I'm going to split the third root right there and the third root right there. And obviously, I could do the third root of y to the 12th. Why? Because I could write it as a power over a root. And that would give me y to the 12th divided by 3, which would ultimately be y to the 4th. Okay, so let me write it down here. Y to the 4th power. No more square roots. Nice, beautiful y to the 4th power. What about the other radical, the third root of y squared? You can't do it, so you just leave it. The third root of y squared. And finally, last but not least, we have the third root of z to the third, which is perfect. That's the right answer, z. So we have z, the nice, beautiful z. Now, if you're thinking, what do you mean z? Well, remember, it's power over root. So you really have z to the 3 divided by 3, which is z to the 1, which you don't need z to the 1. We're just going to write it as z. So looking at the whole problem, that third root problem of 54x to the 6, y to the 14th, z to the 3rd, we split them up and it became like 4 different radical problems. And we did all 4 and we got answers for all 4. Now we just need to organize our answers. Let's write our nice values that were outside of radicals out in the front. So I am going to take the 3, the x squared, the y to the 4th, and the z, and write it together. 3x squared, y to the 4th, z. Okay? And then I'm going to take the third root of 2 and the third root of y squared, and I'm just going to write them together. But I know that if I have the same type of root, which I do, I could multiply them together and put them underneath one single third root. And that's what I'm going to do. Put the third root and put both the 2 and the y squared together, since I know I can't simplify those. Ladies and gentlemen, there is our final answer. I know, you're thinking, man, this is fun. I can't believe this is free entertainment. You're not paying admission for this, right? Amazing. Yeah. Okay. So we need to know how to do that stuff. That will pop out on the quiz this Thursday. And even though the test is on Thursday, you're going to have the same deadline Sunday, 11:45 p.m. Okay? But hopefully you don't wait till then. Let's jump to the actual lesson today. That was simplifying rather challenging radicals. In this section, we're going to be adding and subtracting radicals. Right? We're going to be adding and subtracting radicals. We're also going to be multiplying radicals. We're also going to be dividing radicals. So we're just going to be doing operations with radicals, okay? Now, some of these are ridiculously easy, like adding and subtracting radicals. Okay, so it's similar to adding and subtracting variable expressions, right? If you have 2x plus 3x, because they're the same term, 2x plus 3x equals 5x, you simply add them together. And that's exactly what happens with radicals. It's kind of like treating the radical as if it were a variable, okay? So you could imagine this saying 2 of these x's plus 3 of these x's. It's going to be a total of 5 of those x's. But instead of x's, we have the square roots of 3. What? Yeah, it's that easy, right? It's just combining like terms. You could combine square roots of 3's with square roots of 3's. You could combine square roots of 2's with square roots of 2's. But you can't combine square roots of 2's with square roots of 3's because those would not be alike. It's like combining like terms. So if you're jotting down notes, you might write down adding and subtracting radicals. It's like combining like terms. You could write that down. It's like combining like terms. And that's what I wrote right here in our notes. It's simply combining the radicals that are alike. So even though that's ridiculously easy, not all of them are obviously going to be that easy because easy is boring and we don't want to be bored. We want to have some fun. So let's take a look at this guy right here. Please jot that down. 5 square root of 8 minus 2 square root of 18. I cannot subtract these right now. It's like saying I got 5 apples, I want to take away 2 oranges. You can't do that. They're not like terms, okay? So in any math problem, if you could simplify anything, you simplify it. You make it simple. So the question is, could I simplify anything? And the answer is yes. I could take the square root of 8. That's not a perfect square number. I could rewrite it with multiplication to get a perfect square number. That way, when I split it, I could actually do the square root of 4, which will give me 2. And then, of course, the square root of 2 is going to stay. But don't forget about this multiplication of 5 that's out in the front. So you're going to bring down that multiplication of 5 out in the front, giving us a final simplified expression, 10 square root of 2. All I did was rewrote 5 square root of 8 as 10 square root of 2. And believe it or not, guys, if you happen to have a Casio calculator, I think the Casio calculator could do simplification like this, right? Now, they won't be able to do all of the math operations that we're doing here, especially if you have variables. We will have variables. The calculator can't do it with variables. But right here, I think you could do that one on the Casio calculator, but it's better that you do it on your own and you understand it. Let's do the same for the other one. I'm going to take the square root of 18. It's not a perfect square number. I'm going to rewrite it with multiplication to get a perfect square number. In other words, 6 times 3 is not going to cut it. I want a perfect square number, as in 9 times 2. When I split the root, I will be able to get the answer. Square root of 9 is 3, and the square root of 2 is simply going to come down. Now, let's not forget about this multiplication of 2 out in the front. So let's bring that down, multiplication of 2. And let's also bring down the subtraction between the 2. So what do we really have here? We have 10 square root of 2, take away 2 times 3 is 6 square root of 2. So let me rewrite that. 6 square root of 2. And now that I've simplified both, now I have the same radical, square roots of 2, and now I could actually combine those. So 10 take away 6, final answer will be 4 of those square roots of 2. Ta-da! Fun stuff. Now, sometimes you simplify them and you don't end up with the same type of radical. Like you might have 10 square root of 2 minus 6 square root of 3. Then you just leave it like that. That's your answer, but at least it's in simplified form. So adding and subtracting radicals, it's fairly easy once you practice. Of course, if you're seeing this for the first time, you're like, oh man, that looks complicated. It's not. All you got to do is practice it. It gets a lot easier once you practice. So that is adding and subtracting radicals. Let's jump to multiplying radicals. Multiplying radicals, I think, is easy, but then again, I'm the math teacher. So how do we multiply variable expressions? Well, you don't need like terms when you're multiplying. You could just say like, well, 2x times 3y, 2 times 3 is 6, and just put the x and the y together, right? Same concept here. You do not need like radicals to multiply. You can just multiply the numbers with the numbers and the radicals with the radicals, right? So right here, I'm going to multiply the 2, which is really 2 times square root of 2 times 3 times square root of 8. I'm going to switch the order and multiply 2 times 3, giving me 6. And then I'm actually going to multiply the square root of 2 times the square root of 8. And I'm going to put them together. And luckily, when I multiply 2 times 8, I get 16. And the square root of 16 is 4. So what I really have is 6 times 4. Final answer, 24. Fun stuff with the capital F. Oh yeah. So let's try some more fun problems with multiplication. So like that was pretty straightforward. Multiply the numbers, multiply the radicals, try to simplify the radical. But what if we have this? We have a binomial, 3 plus square root of 2, times a different binomial, 2 minus square root of 10. Again, treat the radicals as if they were variables. So you could like kind of pretend like this was an x. You could kind of pretend like that was a y. But anyway, let's start distributing. A binomial times a binomial, 3 times 2, that is 6. 3 times negative square root of 10, that's kind of like saying 3 times negative x. That'll be a negative 3x, or in this case, negative 3 square root of 10. Does that make sense? Thumb up, yay? Thumb to the side, kinda, or thumb down, like what the heck is going on? Okay, thumb to the side, thumb up, okay. So again, it's like if I had 3 plus x times 2 minus x, what would you do? You would distribute the 3. That's what we're doing here. 3 times 2 is 6. 3 times negative, imagine if it were an x. 3 times negative x is negative 3x. There it is, negative 3x. But instead of x, I have the square root of 10. Okay? Now let's distribute the radical. The radical positive square root of 2. I know that could sound confusing. Just pretend it says like a y, right? Imagine if this were a y. Let's say positive y. Well, what is positive y times 2? That'd be a positive 2y. But instead of y, obviously we have the square root of 2. And then how about positive y times negative, let's say x? All right, just imagine them being variables. Well, a positive times a negative is a negative. But the square root of 2, you could actually multiply that with the square root of 10. You could actually multiply them and put them together underneath one square root. So what is the square root of 2 times the square root of 10? It's the square root of 20. Okay? So this is our answer so far. I'm trying to combine some stuff. Right here I can't. This is negative 3 of square roots of 10. This is positive 2 of a different radical, square root of 2. So that's like saying minus 3x plus 2y. I can't really do that. You could only combine the terms that are alike. So when I go to the square root of 20, question is, that's not a perfect square number. Could I simplify that? Could I rewrite that with multiplication to get a perfect square number? The answer is yes. 4 times 5, split that root. You'll have 2 square root of 5. And I could see that I don't have any other square roots of 5 either. So I have 3 different types of radicals. And they're asking me to add and subtract them, which I cannot do. I could only add and subtract like terms. So what's my final answer going to be? It's going to be 6 minus 3 square root of 10 plus 2 square root of 2, and then bring down that minus sign right there, minus 2 square root of 5. That is a long, disgusting answer, but it is what it is. We could not combine any of those radicals. I hope that makes sense. And of course, if you are understanding this, that's great. If you're not feeling comfortable with this, of course you're not, because you haven't practiced yet. You got to practice by doing the homework in order to feel comfortable with this stuff. Yes, sir.
Yes, sir. Yeah, back to that one. Theoretically, if the positive 2 square root of 2 ended up being a negative 2 square root of 2, theoretically, would you be able to use the subtracting?
What you would be able to do, Jack, is if right here, let's say right here we ended up with negative 3 square root of 10. If over here I had a positive 2 square root of 10, if I had the same square root value, then I could actually combine them. It's that simple, right? It's kind of like combining like terms. X's with X's, Y's with Y's. But in this case, the square roots of 2's, I could combine them with square roots of 2's, and there is no other square roots of 2's. So that's why I have to leave it like this as 4 items in our answer. Now, this next one, you will be able to combine some terms, okay? As a matter of fact, this next one's magical. Yeah, that's right. I said magical. It's like magic. Check it out. Let's copy this down. Let's do this together. We're going to distribute the 3 first. 3 times 3, that's 9. 3 times positive square root of 7, that's like saying 3 times positive x. That'd be a positive 3x. But instead of x's, what do we have? We have the square roots of 7. Okay? And now let's distribute this negative, let's call it negative x if we wanted to. Negative x times 3, that's a negative 3x. But in this case, we don't have a negative 3x. We have a negative 3 of the square root of 7. And then negative square root of 7 times positive square root of 7. A negative times a positive is a negative. Square root of 7 times square root of 7 is the square root of 49. So now I look for items that I could actually combine. Well, we do have a positive 3 of these radical square root of 7 minus 3 of that same radical square root of 7. So if you have 3 and you owe 3, they're like terms. You could combine them. They will disappear. They eliminate. And at the very end, we have the square root of 49. We know that that's a beautiful answer. That's the answer 7. So what we really have here is 9, take away 7, final answer 2. What? Mind blown, right? Now, here's the beauty part. Well, it's already beautiful because the answer came out to be a nice answer without any radicals. Do you guys remember anything like this from semester 1? Do you guys remember a certain word? Right? Look, check it out. We have a binomial, 3 minus square root of 7. We have the same exact binomial, but instead of 3 minus square root of 7, it's 3 plus square root of 7. Do you guys remember that special word from semester 1 when we did complex numbers? Starts with a C. Anybody?
Conjugate?
Yeah, that's Brandon. Give me 5 right here. 5, right? Bam. No, 5. No, 1, 2, 3. 1, 2, 3. Okay. Conjugate. Yes, conjugate, right? Back when we did complex numbers, imaginary numbers, where you had like 5 plus 2i. If you multiplied 5 plus 2i times 5 minus 2i, the imaginary values disappeared. It's the same exact deal here. When you multiply a binomial with a radical in it by its conjugate, it will make the radical completely disappear. Now keep that in mind. Hold that in the back of your mind because we're going to use it and apply it in 3 minutes. What we're going to do now is move on to dividing radicals. Okay? Dividing radicals. Now we already know that we could split the root into numerator and denominator. We could put it back together. We could simplify. But the bottom line is when you are dividing radicals, you do not want to leave a radical in the denominator, okay? So if you're jotting down some notes, write down dividing radicals and put do not leave a radical in the denominator, okay? Do not leave a radical in the denominator. So this problem, it's ridiculously simplified already. So let's pretend I was doing some problem and I get this as an answer, but I know I cannot leave my answer with a radical in the denominator. So I need to get rid of that square root of 3. How do you get rid of something? By doing the opposite. The opposite of a square root? The opposite of a square root is squaring, which is multiplying it with itself. So if I multiply the square root of 3 times the square root of 3, and of course whatever I do to the bottom, I do to the top, it'll get rid of that radical in the denominator. So up on top, I get 1 times the square root of 3, that's simply the square root of 3. On the bottom, I get square root of 3 times square root of 3, which is the square root of 9, which takes you back to the answer 3. So there's your answer. So I just did a simple example of you getting an answer that you can't leave like that. You can't leave it with the square root of 3 on the bottom. You have to get rid of that square root of 3. And how do you get rid of the square root of 3? By multiplying with itself, both top and bottom. Okay? Now, if you try to do that right here, let's say you're working on a different problem, you were simplifying, you end up with this as an answer, you're not going to see that answer on the multiple choice. Why not? Because we do not want to leave a radical in the denominator. Okay, so I would copy this down if I were you guys. Now, if I try to multiply the binomial on the bottom by the square root of 2, that's not going to cut it. It's not going to work. This is where that magical situation of multiplying by its conjugate will completely get rid of the radical. Okay? Let me show you how it doesn't work. Check it out. Don't write this down, right? I'm going to do this wrong. Check it out. If I try to multiply it by the square root of 2, yeah, it'll get rid of it here. That'll give me the square root of 4, which takes me back to 2. But over here, it just ends up moving the square root of 2 over there. So it doesn't work. You cannot get rid of the square root by simply multiplying by the same value when you have a binomial, okay? So what am I going to do here? I'm going to go back. I'm going to erase all this, which is a waste of time. I shouldn't have shown you the wrong way to do it. That's pointless. I apologize. Anyway, what I'm going to do is multiply by its conjugate. That's right. Make it magical. Multiply by its conjugate. Instead of 3 plus square root of 2, it's 3 minus square root of 2. And of course, what you do to the bottom, you must do to the top, 3 minus square root of 2. So let's do the bottom first. Let's distribute. We have 3 times 3, that's 9. We have 3 times negative square root of 2, that's like 3 times negative x. That's negative 3x, but in this case, negative 3 square root of 2. And then we have positive square root of 2, it's like positive x times 3. Well, that would be a positive 3x, but of course it's not x, it's a square root of 2. And last but not least, positive square root of 2 times negative square root of 2 is negative square root of 4, because 2 times 2 is 4. As we could see, the magic happens. Those middle terms are complete opposite values. They cancel out. And on the bottom, what we have left is 9 minus the square root of 4 is 2. So we end up with 7 on the bottom. 7. Nice, beautiful 7 as our denominator. What about the numerator? Well, let's work out the numerator. Over here, we have 2 times 3, that is 6. 2 times negative square root of 2, it's like saying 2 times negative x. That'd be negative 2x, but in this case, negative 2 square root of 2, all over 7. Ladies and gentlemen, we are done. That's my answer. Now, if you're taking a multiple choice test and you get this answer and you don't see it there, they might split the denominator to both terms. So they might write it like this, 6/7 minus 2 square root of 2 over 7. They might write it like this. But I wouldn't actually split it unless I actually could continue simplifying. So for example, if this 7 would have been a 2, then yeah, for sure, put it on both. 6 divided by 2 would give me the answer 3. 2 divided by 2 would be 1. So your final answer would be 3 minus the square root of 2. That's the only time I would actually split it. But I'm letting you know they might split it even though you can't reduce it any further or simplify it any further. So with that said, ladies and gentlemen, we have finished our lesson. And most of these simplifying questions could be done on the calculator. Well, not most, but some of them. But what the calculator can't do is do that simplification with variables like on our homework. Some of them have pure numbers, but yeah, some of them have variables. Calculator can't do that. So that's why we practice with this homework. So ladies and gentlemen, I do apologize. We are out of time. The videos for the homework are already posted. If you need help on that homework, of course, the solutions are there. Try to do it. The only way you're going to understand this, or the only way it becomes easy,